Welcome back to lecture 17.2, where we're going to talk about perpetual motion and entropy. So last time we talked about Carnot cycles. We talked about the efficiency of a Carnot cycle and how all Carnot cycles have the same efficiency, right? And otherwise, you would be able to extract heat from a cold reservoir and dump it into a hot reservoir without doing any work, okay? So the second law, we actually got our Carnot cycle from thinking about our second law, and they're really intimately related. So often, when we think about the laws of thermodynamics, maybe people will bring up the idea of a perpetual motion machine. And then let's try to see if we can clarify what the first two laws of thermodynamics say about perpetual motion machines. So a perpetual motion machine means one that runs forever. And is this possible? Okay, so what does the first law say? Well, the first law says, remember, it's basically a statement of conservation of energy. So what does that say about a machine? It says that you cannot make a machine that produces more energy than it consumes. And by energy, really, I mean things with the units energy, work or heat, right? The total energy. Okay, but the second law actually says something more stringent, right? And it actually says that you cannot make a machine that runs forever. That runs forever without inputting energy. So think back to our Carnot cycle. Our Carnot cycle always had an efficiency less than 1, right? You could never make a perfectly efficient machine. And so you're always, if you want to do work, you're going to have to be inputting heat from a hot reservoir and dumping it to a cold. Or if you want to have a heat pump, you're always going to have to be inputting work. Because you can never have an efficiency of 1, you cannot have a machine that runs forever. So this is really interesting because now this statement that the efficiency of a Carnot is always less than 1 has profound impact on the idea that everything eventually runs down, right? You start a process, and because the efficiency can't be 1, it's always going to run down. And this implies a direction, a direction in time. It sort of suggests time's arrow, right? That things go one direction, right? And eventually run down, and they don't go the other way. So we've already seen this a couple of times. Let's imagine the following scenario. We had a cold reservoir and a hot reservoir. So imagine we had an insulating partition where, let's say, T1 was greater than T2. Then heat would flow across that barrier, right? Until we got to a final uniform temperature, right, which we called equilibrium. So heat spontaneously flows from hot to cold, but not cold to hot. That is, this process is irreversible, right? Remember that the interesting thing about this is this process is not irreversible. It always seems to go one direction. It's sort of like this running down. It has a direction in time, right? Except, it wouldn't violate the laws, the first law, right? The first law was a conservation of energy argument. I moved some energy, a heat over here, right? But moving it back would not violate the first law, okay? It's really the second law, which is suggesting that I can't do this kind of thing. This is sort of a macroscopic thermodynamic law, but you could imagine even the same thing microscopically. We did our free expansion problem, right? So imagine free expansion, where we go from gas on one side spontaneously to gas on both sides. One of these can happen, right? But there is no free contraction or compression. Right? We can have free expansion, it can happen spontaneously, but there is no free compression. Let's do a similar one. You can imagine mixing two processes, right? So imagine I have two different kinds of things and allowing them to mix up, right? I mix them up, I get some homogeneous mixture, right? But I can't spontaneously unmix, right? There's no free or spontaneous unmixing. There's certain processes which seem to be irreversible. Actually, there's a really nice figure from another book on low temperature physics that I like on this concept of no free or spontaneous unmixing. I'll actually see if I can stop and splice that in. Here's a nice figure from The Quest for Absolute Zero by Kurt Mendelsohn, where you can see that if you had a container full of red and white sand, and you were to do an experiment where you very carefully mixed the two together, you would never be able to reversibly unmix the two. So hopefully I spliced that in right there. And so what we're going to ask is now, is there a way to categorize this or quantify? So can we quantify this tendency for one direction? This tendency for certain processes to happen in one direction, but not another. So, yes, we're going to actually define this. So this is going to define or we're going to make up a quantity. So let's make up a quantity or imagine a quantity that characterizes the tendency for a system to evolve in only one direction. So let's imagine this quantity and let's just call it the entropy. And we're going to give that the letter S. Okay? So, so what do we want? What do we want from S? So we know that the change in S should be not zero for an irreversible process. All right, that is, for some process, we're going to increase in this quantity S. All right, so these would increase the entropy. So this state is going to have more entropy than this one. This state is going to have more entropy than this one. This state is going to have more entropy than this one. And then but the change in entropy must be zero for a reversible process. And that in a process that delta S is going to be greater than or equal to zero, right? So we're going to never have negative entropies, right? We're not going to have things that go backwards, so irreversible processes which can be undone. So a process is either going to be zero for a reversible or positive for an irreversible process. So we're really thinking about this from a macroscopic perspective, and that's really cool because next semester in Stat Mac in 311, you're going to really think about entropy from a microscopic perspective. So an entirely different way of thinking, but these are going to actually be the same thing, and actually it's a really cool link. That is that entropy is really, in the microscopic world in Stat Mac, it's about counting up quantum states. It is really a measurement of the number of quantum states. It's really about counting. It's really about quantum states. So the entropy, we've been doing all this thermodynamics with macroscopic quantities, heat and temperature and work and internal energy. But now we're going to define an entropy, and it's going to be the bridge basically between all those these macroscopic thermodynamic states and those microscopic quantum states. It's really going to be the bridge. So that's what entropy is going to be, and so you'll see that again next time. So, you'll see that bridge really clearly in 311. Okay, so now let's imagine building a system like this, okay, that has these properties. Okay, so let's imagine our Carnot cycle. So let's look back at our Carnot cycle. Which was, by definition, reversible, right? So we're going to want a quantity which is zero in a Carnot cycle. So both in the loop, right, the whole loop was reversible. But moreover, every path was reversible. Okay, we need, so this is a good way to start to think about, so think about our Carnot cycle. We had our isotherms, we had our adiabats. So, what was reversible? What was, that is, what quantity, so what quantity is zero in both, let's call it A and B. So this is A and this is B. So we need to satisfy both of those. What quantity is zero in both of those? So let's think about our first isotherm. So actually, was the work zero in our loop? No, so our work in our loop was not zero. So that's quite a problem, right? That was the network. You know, we had heat in, we had heat out. So there was no heat along our adiabats, but there were heat along our isotherms. So the heat doesn't satisfy B, right? That it's zero in B. We can't say that about our internal energy, right? So along the adiabats, the internal energy changes because we do work. The temperature isn't zero. So what is it that could be? Well, let's imagine something we learned. We learned that along the isotherms, we had QH over QC is equal to TH over TC, right? Sorry, that for our process, for our whole Carnot cycle, we could define that. Let's just rearrange it a little bit. So let's put QH over TH equals QC over TC, or QH minus TH. Sorry, QH over TH minus QC over TC is equal to 0. This wasn't along the isotope, it's for the full loop. Okay, so well, it's actually not for the full loop, it's for both isotherms. That's what I really mean to say, for both isotherms. All right, that this was our relation that was connecting our isotherms. Okay, so along the isotherms, we had this relationship between QH and TH. So this would suggest that in those processes, right, that along the isotherms, this is 0. But what about the adiabats? Along adiabats, dq was 0, right? So q over t is by definition 0. And that means along the entire loop that qi over ti is equal to 0. That anywhere along the loop, in any process, Qi over Ti was 0. So it'll both in each process and along the loop. So let's just change that. Sum to be more general. So more generally, if I have some process, right, along some closed loop, then the integral of the heat, so R means that this is reversible, and this means you're going to integrate around a loop. Let's call it a closed loop, to be more clear. So, more generally, we now have a term which satisfies what we wanted to say about our entropy. Okay? So next time, we're going to explore this quantity, dq over t, a little bit further.